In Chapter 11, we are looking at nuclear energy. This is a process that some people view as a viable energy option, as an alternative to electricity and fossil fuels, and some people view it as dangerous, associating it with accidents and nuclear weapons. We're going to be looking at two processes, fission and fusion, that produce nuclear energy. First, starting with nuclear fission. This is the process of splitting a large nucleus into two smaller nuclei, and it's done by bombarding it or hitting it with neutrons. So a nucleus is bombarded with neutrons. And this causes it to break apart. When it breaks apart, it sends out more neutrons. These neutrons in turn hit other nuclei, causing them to break apart, and so on. This causes a chain reaction. For example, if we had uranium-235 and we bombarded it with neutrons, so here's plus a neutron, it would temporarily incorporate that neutron, so absorb that neutron into its nucleus, become uranium-236, but very temporarily, for like a millionth of a second. And then it would break apart into two smaller nuclei, which I'm just going to write as N1 and N2, plus additional neutrons. And the star here is to make a note that uranium-236 exists only briefly. Here pictorially is that same reaction. So we have uranium-235 and it's being hit by a nucleus or a neutron. That neutron gets absorbed temporarily. We have unstable uranium-236. So that's going to break apart. We're going to get two smaller nuclei, N1 and N2, and these additional neutrons, which are then going to go shooting off and can potentially hit other nuclei if there's other nuclei around. I'm going to write out this example again using a real example with actual product nuclei. So we have uranium-235 being hit by a neutron. It could break apart into barium-141 and krypton-92 and 3 additional neutrons. There are rules for writing nuclear equations, and they are as follows. First, you need to conserve the atomic mass. So there's a conservation of atomic number. I said atomic mass, I meant to say atomic number. So this is a conservation of electric charge. And there's also a conservation of the mass number. So the total number of protons and neutrons is conserved. Looking at the above equation, so if we look at conservation of atomic number, we have atomic number of 92 on the reactant side. Over on the product side, we have 56 plus 36, which equals 92. For mass number, we have 236 plus 1, or 235 plus 1, so that's 236. And then over on the product side, we have 141 plus 92, which would be 233, plus 3 here, so 236 in total. And it needs to be noted that although the mass number is conserved, the mass is not. A tiny amount of mass is converted into energy. So a tiny amount of mass is converted into energy. Looking at a sample problem with some numbers for this, if we wanted to figure out the amount of energy produced when 3.090 times 10 to the negative 28 grams of mass, we use Einstein's equation, E equals mc squared. E is for energy, m is for mass, c is for the speed of light. So our mass was 3.090 times 10 to the negative 28. Multiply that by the speed of light, 3.0 times 10 to the 8 meters per second squared, and you get 2.781 times 10 to the negative 11 joules. In an uncontrolled chain reaction, there's a very rapid release of a lot of energy, and this causes an explosion. This is what happens in nuclear bombs. But if you have a controlled chain reaction, then the rate of neutrons produced equals the rate of neutrons being used, and this can be used to generate electricity. Like in nuclear reactors. That's it for 11.2. We're going to flip over the page now and take a look at 11.5. 11.5 deals with nuclear fusion. These reactions are the opposite of fission because they're joining two nuclei together, so two small nuclei join together to make a larger one. And these reactions occur in the sun, and they supply the energy needed to sustain life on Earth. So nuclear fusion is the joining. Got to put the pen on here. So it's the joining or the fusing of two small nuclei to make one or a larger nucleus. And this process gives off a lot of energy. An example that happens in the sun would be if you had hydrogen and hydrogen joining together to make helium-2. This is unstable and breaks down right away, but that's the example that I'll use. In this process, in fusion, atomic number and mass number again are conserved. The mass of the product is a little bit less than the sum of the masses. Loss of mass is converted into energy. So loss of mass is converted into energy. And is released. In order for fusion to occur, the nuclei have to collide at very high speeds. So nuclei must collide at very high speeds. And for these very high speeds to be met, it requires an extremely high temperature. We cannot reach these temperatures here on Earth, but if we did, we could create a lot of energy from it. Looking at an example with some numbers, if we wanted to calculate the energy produced when 7.000 times 10 to the negative 30 kilograms of deuterium undergoes nuclear fusion, we would again use E equals mc squared. For M, 7.00 times 10 to the negative 30. C is 3.0 times 10 to the power of 8 squared, and you're going to get 6.3 times 10 to the negative 13 joules. This is an incredible amount of energy for a single atom to produce. The last topic here in nuclear fusion is nuclear fusion weapons. And it was discovered that the fission bombs produce temperatures that are similar to that of the sun's core. So it's incredibly hot inside a fission bomb. And because of that, fission bombs could be used to start a fusion bomb. And these are sometimes called hydrogen bombs, or thermonuclear bombs, or the atomic bomb. That's the end for the notes for 11.5.